Today we will be covering limits at infinity. So what is a limit at infinity? A limit at infinity is defined by the limit as x approaches infinity of f of x equals L. So the values of f of x are getting arbitrarily close to L, the horizontal asymptote, as the values on the x-axis are getting larger. Now if the limit of x approaches infinity of f of x equals L is true, then y equals L is the horizontal asymptote. So before we begin some practice problems, here are a few quick reminders. When r is greater than 0 and is a rational number, the limit as x approaches infinity of 1 all over x to the r equals 0, and the limit as x approaches negative infinity of 1 over x to the r also equals 0. And this is because when we divide a number, such as 1 by infinity, the number is divided so much that in the end there's essentially nothing left. So the limit as x approaches infinity of 1 over infinity to the r equals 0. The first practice problem is a more basic problem to remind you guys who are reviewing for the midterm about the general procedure. So the problem is the limit as x approaches infinity of x cubed plus 6x squared minus 4 all over 3x cubed plus 14x. So what we want to do now is divide the numerator and the denominator by the highest power in the denominator, since we have an indeterminate form. So the highest power in the denominator is x cubed. So the next step would be the limit as x approaches infinity of x cubed over x cubed plus 6x squared over x cubed minus 4 all over x cubed. So I'm dividing by x cubed. So 3x cubed over x cubed plus 14x all over x cubed. So the reason we're dividing by x cubed is because we're trying to get the form 1 over x to the r, because as I explained earlier, it's equal to 0 as x approaches infinity. So now we're going to simplify this. So this becomes the limit as x approaches infinity of 1 plus 6 over x minus 4 all over x cubed x cubed all over 3 plus 14 all over x squared. So these will go to 0 because of the rule I mentioned. So the limit of the function is 1/3. Now we can check our answer by using algebra, because we know that when the denominator of the degrees in the numerator are equal to that in the denominator, the horizontal asymptote equals the ratio of the leading coefficients. And if the degree of the numerator is greater than the degree in the denominator, there are no horizontal asymptotes. But if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote equals 0. So from our original problem, the highest degrees of the denominator and the numerator are equal, so you take the leading coefficients, which were 1 over 3. The second practice problem is the limit as x approaches infinity of 3x minus 2 all over the square root of 2x squared plus 1. Now in solving this kind of problem, we need to remember that when we divide the top and the bottom by the highest power in the denominator, the square root of x squared equals x when x is greater than 0. So the next step would be the limit as x approaches infinity of 3x all over x minus 2 over x all over the square root of 2x squared plus 1 all over the square root of x squared. Now I wrote this step, this is an extra step, and it's just to show you guys that the square root of x squared equals x. And now, so you go to the limit as x approaches infinity of 3 minus 2x, I'm just simplifying this, all over the square root, now you can write it all under one larger square root, of 2x squared all over x squared plus 1 all over x squared. So that equals 3 minus 0 all over the square root of 2 plus 0, which equals 3 all over root 2. So this is the same problem as before, but now it is negative infinity. So now that this problem is the limit as x approaches negative infinity of the function, x is approaching negative infinity, therefore we need to plug in negative numbers. So the square root of x squared equals absolute value of x. So let's talk about this for a second. When we plug negative numbers into the square root of x squared, we always get positive numbers. For example, plugging in negative 3 will produce positive 3 because negative 3 squared is 9, and then the square root of that is 3. However, since we're dealing with numbers less than 0 as x approaches negative infinity, x is negative. So what does this mean? So let's start this problem again. So the limit as x approaches negative infinity, we need to make the denominator in front of the square root negative to satisfy this condition. So the answer is going to end up being, instead of 3 root 2, it's going to end up being negative 3 over root 2. So the next problem is the limit as x approaches infinity of the square root of x squared plus x minus x. In order to get a fraction so that we can divide the top and the bottom by the highest degree in the denominator, we need to multiply by the conjugate. So that's going to get us square root of x squared plus x all over the square root of x squared plus x. And when we simplify that, we get the limit as x approaches infinity of x squared plus x minus x squared all over the square root of x squared plus x. And these cancel out the x squareds, so we end up getting this. Now we divide by the highest degree in the denominator, which is the square root of x squared, or x. So the limit as x approaches infinity of x over x all over the square root of x squared all over x squared plus x all over x squared plus x over x equals 1 all over the square root of 1 plus 0 plus 1, which equals 1/2. This next problem applies limits at infinity to the squeeze theorem. So the problem is the limit as x approaches infinity of 1 over x times sine x. So first we have to write the restriction of sine. So to continue the problem, we multiply everything by 1 all over x in order to get the original function. So that will be negative 1 over x is less than or equal to 1 over x times sine x, which is less than or equal to 1 all over x. So now we take the limit of everything. So the limit as x approaches infinity of negative 1 all over x is less than or equal to the limit as x approaches infinity of 1 all over x sine x, which is less than or equal to the limit as x approaches infinity of 1 all over x. So because this is the limit as x approaches infinity of 1 all over infinity, this goes to 0. So this is 0 is less than or equal to the limit as x approaches infinity of 1 over x times sine x, which is less than or equal to 0. So since, according to the squeeze theorem, if the limit of the function is in between the outside functions and the outside functions equal each other, which they do, they're both 0, then the limit as x approaches infinity of 1 over x times sine x also equals 0. So that is how we can use limits at infinity with other concepts we've learned this quarter.